Hi pre-calculus students. This video is an introduction to sequences. So it's going to cover basic definitions and notation so we can hit the ground running next class with some practice and applications. So to start, before I give any notes, what I'd like you to do is copy down these 4 different patterns, leaving a little bit of space underneath each one, and then just pause the video and try to identify what is the pattern in each of these different sequences of numbers. Okay, so hopefully by now you've paused the video, identified some patterns, jotted down some ideas. So maybe for the first one you said something about adding 3 to get the next term. Here maybe you said something about multiplying by 2. For the third one maybe you said that the denominators of the fractions were perfect squares, or something like this. And then the last one maybe you said something about how you're adding 1 to the numerators and to the denominators. But basically all of these are examples of what we're going to call sequences. So all of these are examples of sequences. Sorry, I had a spelling mistake, but that's an E right there. So now we're going to basically define a sequence, but a sequence is essentially just an ordering of numbers that create in a pattern. And we're going to define this in terms as a function. So we would say, and I'm going to define an infinite sequence. So an infinite sequence is a function. And our understanding of a function is that there's an input and an output. So it is a function whose domain, which would be the inputs, is the set of positive integers essentially what we're saying there is like we can kind of count, this is the first, the second, the third, the fourth term. And that is essentially our input values. And so we're starting with the first term. So that means starting with 1, 2, 3, etc. So that's positive integers. And then the function values. And this is a little bit of notation. We're going to kind of describe our function values to be a sub 1, a sub 2, a sub 3, a sub n. Okay, these are going to be what we're calling our terms in our sequence. I meant to write terms in black. So these are the terms of the sequence. They're also the outputs, if we think about it in terms of a function. So to kind of connect this definition to an example, it's this idea, and I'm going to kind of look at the very first pattern we looked at and turn it into a kind of input-output by making a t-table. So if I kind of separate things out along like this, then my inputs, I'm going to call n, are just the positive counting numbers, 1, 2, 3, 4. And then my outputs, which are the numbers in the pattern, would be my a sub n values. So it's this idea that when n is 1, we get the a sub 1 term in our sequence, or the first term in our sequence. So this would be a sub 1, this would be a sub 2, a sub 3, a sub 4. And it's really, the meaning of each of these is just the 4th term in the sequence, the 3rd term in the sequence, the nth term in the sequence. And now we can kind of see the connection between just a pattern and an actual function and this definition. So one quick, so a little bit more vocabulary, we would say sequences can be defined with 2 different types of formulas. So we have with an explicit and something called recursive formulas. And we're going to look at examples of both of these things. These words might be familiar to you from Algebra 2 or another class. But first we're going to talk about explicit. So an explicit formula is defined in terms of n. So it is a formula that if I know what n is, I could plug in the value of n and get an output, which would be the nth term in the sequence. So an example would be if I said a sequence is defined by a sub n equals -4n minus 2. And then I could write the first few terms in the sequence. So like the idea there being the first term in the sequence, a sub 1, is just let me plug in 1 for n. So if I plug in 1 for n in this formula, -4 times 1 minus 2, I get -6. And I can keep going by plugging in 2. And -8 minus 2 is -10. Plug in 3 for a sub 3. And we get the idea. We are generating the numbers in this sequence. The nice thing about an explicit formula is I could get the 100, that when n is 101, I could plug in 101 and know exactly what the number is in the sequence without having to write out all 100 terms coming before that term. Okay. Another thing we can do with explicit is, so here I gave you an explicit formula. We could generate the sequence. Another thing that might happen would be to write a formula for, and let's use our first sequence above. So if we were to write a formula, and I'm going to say, sorry, an explicit formula. And then I guess I need an n here. An explicit formula for 2, 5, 8, 11. So it might be, if we're trying to write an explicit formula, we're trying to relate the input values n's to the outputs, which are the numbers in the sequence. So it might be helpful to kind of slide back up and look at this table and think, what's the relationship between 1 and 2, 2 and 5, 3 and 8? How can I plug in my n values and get out my a sub n values? One thing to notice is we know we're adding 3 each time, so we know this is kind of linear, or our rate of change is 3. So I might think, oh, there is a slope of 3. So, well, one thing I notice is 1 times 3 is 6. I'm sorry, 1 times 3 is 3, minus 1 is 2. 2 times 3 is 6, minus 1 is 5. So I'm kind of saying, oh, well, if I multiply my n values by 3 and then subtract 1, I get exactly these function values. So I'm going to propose a sub n equals 3n minus 1, which is what I'm writing right there. Okay, so we're going to kind of also talk about some other strategies for creating a explicit formula, but for now I want you to try 2 problems. So you're going to pause the video to try these problems and then press play. So your you-try problems are going to be, the first one is to write the terms in the write the first 3 terms in the sequence. And I'm giving you a sub n equals 4 plus -1 to the nth. So this is going to be a not linear sequence, but see what happens. And then the second thing I want you to do for the you-try is to write an explicit formula. And we'll say for, let's do the third pattern from above, which was 1, 1/4, 1/9, 1/16. See if you can come up with an explicit formula there. So pause the video, press play once you're ready to move on. And I'm just going to move right on. Okay, so that's explicit. The last part of the video, I'm going to talk about recursive formulas. So a recursive formula is defined in terms of the previous terms in the sequence. So the idea of this, when we're thinking about the notation, if we think about we have some a sub n term, we also have the next term after that, which would be the a sub n plus 1, or the term right before it, which would be a sub n minus 1. So I'm just kind of like, so we can kind of recognize what the meaning of each of these are, I'm going to kind of label them. So we're calling a sub n a term in the sequence. A sub n plus 1 meaning the next term. And a sub n minus 1 being the previous term. Okay, so then I can define a function purely based on the terms that come before it. So I could say a sub n equals 3 times a sub n minus 1 plus 2. The meaning here is let me take the previous term, multiply it by 3, and then add 2 to it. But if I'm giving you something like that, I'd have to give you a starting term. So we could say for a sub 1 equal to 5. And I also need to put a little bit of a restriction on what n can be, because n couldn't be 1 here. Because if n is 1, then I have the 1 minus 1 or 0th term here. And I don't have a 0th term in my sequence. I'm starting with the first term, right? So that's the meaning of this restriction, and then this is to get me started. So if I were to write the terms in this sequence, I'd say, okay, well, starting with the first one, it's 5. I was given that. To get the next one, the second one, well, that's my nth one, so I do 3 times the previous one. Well, the previous term was 5, and then I'm adding 2 to that. So 3 times 5 is 15, plus 2 is 17. Now to get the next one, I do 3 times the term right before it, which is the second term. So I'm taking 17 now and adding 2 to that. So now 3 times 17 is 51 plus 2 would be 53. And I could keep going like that. The only thing about an explicit, a recursive function is this is only, I'm kind of going in sequence. So it's a lot harder to take this and say, what's the 101th term? Because I'd have to actually write them all out. Another quick example would be, just to show you a slightly different notation, I could also define a function. I'll just actually do the same exact function to say a sub n plus 1 equals 3 a sub n plus 2 for a sub 1 equal to 5 and n greater than or equal to 1. So now notice this is the same sequence. The next term is 3 times the previous plus 2. I'm still having the same starting term. Now I'm saying n is greater than or equal to 1, because now n could be 1. So I start, like when n is 1, that gives me my second term. And notice this is just a slightly different way of saying the same thing, and it should generate the same sequence. So now, some utry problems. So your first utry is going to be, calling this utry C because we already had an A and a B. To write the first 4 terms in the sequence, if I give you a sub n plus 1 is equal to 1/3 a sub n for a sub 1 equals 9 and n is greater than or equal to 1. So can you write the first 4 terms in that sequence? And then part D is, can you come up with a recursive formula for the second pattern in the beginning of our notes for 2, 4, 8, 16? What's the recursive pattern there? And we will be building on this next class.